This video, we're going to talk about intermolecular forces and potential energy and the strength of ionic compounds relative to bond energies and bond lengths. So we discussed already a little bit about the strength of ionic bonds versus covalent. By definition, usually ionic bonds are quite strong. In fact, they are extremely, very strong compared to covalents, with exceptions of a couple of covalent bonds. And the reason why is because, again, they have this lattice structure that attracts electrons very well. So ionic bonds are so strong that they usually require a lot of energy to melt them down. So if I have a crystal like NaCl as an example, and table salt, and I want to vaporize that into gas, ions, chlorine, and positive charge sodium, it's going to require an energy of about 788 kilojoules per mole, which is extremely high. This basically means the delta H indicates the delta H lattice. And so this is an enthalpy specifically value that tells you that if I want to break down this crystal structure, I have to input a positive value. So positive values indicate an endothermic reaction. Now, what are some factors that affect ionic points and melting points? So if I want to melt down sugar as an example, what I want to do is determine Coulomb's law. And Coulomb's law, by definition, tells you the attraction between two forces of these atoms. So if I want to look at the distance between, let's say, NaCl of a positive and a negative charge, I want to look at the Q value. And the Q value indicates the charge of that single ion, while D represents that distance. And you multiply it by K, which is going to be a constant, and it's going to give you the force. Now, what you need to really understand is that the closer something is, the stronger that attraction becomes, especially for ionic solids. The second thing you also want to know is that the distance between those also matters. The further away that distance is, the more likely you're going to get less of a force of attraction. Alright, so here's a classic example of melting points of ionic solids specifically. So the question is, which compound from each set has the greatest melting point and why? So if I were to ask you between LiF and LiI, why would LiF versus LiI have greater melting points versus some of the following? And the big question is why, and how do we go about explaining that? Alright, so the first thing is, let's take a look at the overall charge for lithium. So lithium is a positive 1, and fluorine is a negative 1. Same thing with Li and I. The problem here is that since they're both similar charges, now we have to take a look at the distance between them, and specifically the radius of each one. So if you take a look at fluorine, fluorine has a smaller radius than Li, while iodine has a larger radius than I. So if we take a look at the first example, F minus is smaller than I minus. And in this second case, if we take a look at magnesium and chlorine 2, this is a little different story because magnesium and chlorine are going to have different charges. While in oxygen you have a negative 2 and magnesium has a positive 2. And so in this case we're looking at the Q value for Coulomb. So in this specific case your Coulombic charge is going to be greater on this side because it's negative 2 plus 2, which gives you a negative 4. Here it gives you plus 2 minus 2, which gives you a negative 2 charge. So in this case, magnesium oxide is going to have a negative 4 greater charge. Now, second thing with NaF and MgI, so here we're taking a look at now the cation. Sodium has a positive 1, magnesium has a positive 2, and if you take a look at the charge overall, it's negative 1 and negative 1. So in this case, greater charges are always more significant than smaller distances. So if I had a choice between these two, I'm always picking those. So as an example, if it's something that's a smaller radius, it's going to be more attractive. So we predict that LiF is going to have the greater melting points. In this specific case, we predict that MgO is going to have a greater melting point because it's greater. And in this specific case, we're going to predict that MgI is going to have a greater melting point because it has a larger distance, larger charge, than I2. Alright, so here's the secondary question is melting points of ionic solids. Which of the following metal fluorides would have the highest melting points and why? So let's take a look at this example here with metal fluorides. This could be in any sort of metal, but we're taking a look at the radius. So fluorine is a small one here in the red, and the blue one indicates any sort of metal. So the question is, if I were to give you this representation, which one would have the highest melting points? Obviously, we're dealing with specifically the radius. So we're looking at that force of attraction between those two. So our answer would have to be B would have a higher melting point, and the reason why is because the charges here are +1 for both. But the metal, cation B, has a smaller radius, which means that the attraction is going to be greater. And because of that, you're going to have a higher melting point. So if I try to melt these two things down, one of them is going to be at a higher temperature than the other, B specifically. Alright, now let's talk a little bit about bond energy and what does bond energy represent. So bond energy is the potential energy of valence electrons that decreases as they approach the nucleus of another atom. So remember that if we increase that distance, we decrease the energy, the force of attraction. But what they have is that they have this thing called high potential energy. And so if we actually lower that potential energy and they get a stronger attraction, then we're going to automatically create a higher force. So potential energy is kind of like this idea of like going up a roller coaster, and as you're sitting on that roller coaster, you have the ability to take that energy and turn it into kinetic. And kinetic energy is more about this idea of like actual force being used. So although they are far apart, they have high potential energy because they have the potential to get closer. But here, they already have low potential because they're already close. So that's the best way I can kind of explain it. Now, normally bonds release energy during the formation of a bond. So if I want to make a bond between something like CH, I'm usually going to release energy. Potential energy decreases as the atoms move closer together. So if I start getting closer and closer and closer, we're going to decrease that potential energy, obviously, because now they're already exerting a lot of force of attraction. However, the same amount of energy must be added in order to break that specific bond. So if I want to go ahead and break a bond, I gotta put some energy in. And that kind of makes sense because when you're forming a bond, it releases energy because there's less potential energy. But if I want to break a bond, I'm actually giving more potential energy, which means I have to increase that to move them away from each other. And so the amount of energy that's required to break the bond between two specific atoms in a molecule is equal to the amount of energy that's released when a bond forms between those two atoms. So it kind of makes sense according to that law of conservation of energy. So if I want to break a bond, I got to put energy in, and the same energy will get released when I form a bond, and I can actually calculate that using a numerical value. So if I take a look at something like HCl as an example, HCl, if I want to make HCl as a bond, I want to break them together from H and Cl, it's going to require positive 432 kilojoules to break it between hydrogen and chlorine. However, when I take a look at the other way and I want to push them together, then what's going to happen is that it's actually going to release energy because that's actually less potential energy. So you actually form more energy by putting in bonds when the hydrogen and chlorine are formed. And here's a classic example of that energy as we're talking about that. So on the y-axis, you have how much energy you have kg per mole. So obviously, the more negative that number is, the more likely there's the likelihood of a bond forming. So at the very bottom of this chart you see right here, this tells you that at negative 458 kilojoules per mole, hydrogen and hydrogen will combine, and this distance is exactly 0.074 nanometers. Now if I increase that distance a little further, you can see that the potential energy actually increases, and now hydrogen no longer is bonded. But as the distance becomes smaller and smaller and smaller, then you can kind of see where the optimal point is, and that usually would indicate also your distance between them. Question is, why wouldn't you actually have here? Well, the problem is that if you get them too close to each other, you're not going to get that bond formation. So again, that little dip that we see here, that's how much energy is really given off when they actually form that bond. And so scientists like to use this to figure out the exact distance of these bonds and how close they are to each other. So, and in summary, let's go ahead and talk about potential energy decreases as attractions between the nuclei and the valence electrons pull the atoms closer together. At 0.074 nanometers, the bond length of H2, the energy is at the lowest point, and that's why H2 exists on average. So if you think about bonds, they can be thought of as springs. They're not really like consistent, meaning that they're not static. these bonds are actually going to be at the midpoint of that oscillation. So they're kind of going back and forth like one of those slinkies, you want to call it. And 0.04 is going to be the optimum part. Now, the further move to the left, the spring is compressed and the potential energy rises. So basically looking at that chart again. Now, if the atomic radius of the bonding atoms increases, the bond length increases as well, and the bond energy decreases. So again, if you have a very large distance between these two, you begin to logically make these bonds longer and longer. The closer proximity they are, the greater that force of attraction between protons and bonding. When the force of attraction is greater, it requires more energy to break that bond. So again, just kind of going back on this idea, radius versus bond energy. All right, so here's an example of something that you will definitely need to know. Here is bond energy versus bond length. So CCl is a single bond. It has a bond energy of 339 and it has a bond length of 0.177 nanometers. So if you take a look at each of these three bonds, you can kind of see that as you are changing the halogen, you actually get a different bond energy. So it seems like chlorine, and we already know because chlorine is a smaller radius, it's going to be closer to C. The bond length gets closer, and then the bond energy gets a lot higher. So if I want to form this bond, it's going to form 339 kilojoules. So as the atomic radii increases, the bond length is going to increase, PE increases, and the bond energy decreases. So again, it's kind of like it's all interconnected. It's really interesting to see that you can actually create more energy if you can figure out which atom is going to be connected. All right, so let's take a look at a couple examples here and see if you guys understand. Consider the space filling models below. Which molecule has the least amount of PE associated with each bond? Which bond has the lowest bond energy? Okay, so the first thing is we want to take a look at the size of the shell. So the first thing is if you take a look at red versus this gray one, the red one actually has a smaller bond, and the one in gray has a bigger one because the radius is bigger. So if I were to pick, I have to take a look at how big the size is. So we already talked about that the distance between these two would indicate how large these are. So lowest PE, as it has the shortest bond length, which means that they're going to be closer together, which means this bond is going to be higher. And this one has the lowest bond energy as it has the longest bond length. So we're talking about PE, it has the lowest, and we're talking about the lowest bond energy will be this one. All right, so let's talk about single bonds, triples, and doubles. So as the number of bonds between atoms increases, the bond length decreases, and the single bond energy increases. So a single bond versus a double and a triple. So triples actually have to be really close together. And again, because of that, the density of the electrons are going to be in a much closer area, and they're going to be pulled in between these two atoms. So generally speaking, triple bonds are going to have a lot more energy than something like a single bond because the protons are a little farther away. So as a general rule, let's take a look at bond energies. So F2 is a great example of this. F2 is a single bond, and it has a bond energy of 155 kilojoules per mole, and the bond length is, I'd say it's, fairly in the larger side. And again, the reason why is because they're farther away, the bond energy is less. But if you take a look at your triple bonds, take a look at that one. That's actually a very small bond length, but it has a very high bond energy. So N2 actually packs in a lot of energy. So as the number of bonds between two atoms increases, the bond energy increases and the bond length decreases and the PE decreases. So if I were to take a look at things like explosives as an example, N2 is definitely a better choice when you form N2 bonds. It's because the amount of bond energy that you're forming with an N2 is much higher than an F2 because of the bond length that we're dealing with. All right, so if we take a look at bond orders, we're taking a look at the number of bonds between the atoms. So when the bond order increases, the bond length will decrease, and the P associated will also decrease, and the bond energy increases. So if we take a look at the bond order for triples, it's a 3, 2, and 1. We're definitely going to have more energy and a shorter distance between those two. All right, so here's a question for you. Consider the ball and stick models below. The carbon-carbon bond in which molecule has the lowest PE? The carbon-carbon bond in which molecule has the lowest bond energy? So again, let's make sure we understand the difference between PE or potential energy versus bond energy. So in this specific case, we have carbon-carbon bonds, triple bond specifically here, and a double bond. So because this one is a triple bond, it's going to have more energy. So the lowest PE, as it has the shortest bond length, and this one has the lowest bond energy as it has the longest bond length. So it kind of makes a little bit sense, right? Because they're closer together, they have lower PE, and because of that, this one's going to have a lower bond energy. Alright, so just to show you guys a little bit about ball and sticks and different ways to represent models. So space filling is what I showed you guys earlier, where you get two balls with different colors. They show relative bond length. It does not show the 3D positions very well. Ball and stick is like the one I showed earlier. You can see double and triple bonds, and they usually are not proportional and greatly exaggerated to show that. Alright.